Greetings engineers. In this hands-on workshop on AutoPipe, we'll learn how to model, analyze and design this piping system. As you can see on the model on the screen, we'll model pipes, bands, anchors, vertical supports and guide supports in this model. We follow the ASME B31.3 code, and we include gravity load and thermal loads and pressure loads in this model. And the pipe size for the whole model, we use just the 200 mm diameter pipe, temperature 370 degrees Celsius and pressure 1.7 Newton per millimeter square, and A53 grade B material, specific gravity 1, and we'll skip the corrosion and insulation allowances. So this pipe run have an anchor point at this A00 point and A09. So only two anchors, and total length of this pipe in minus Z direction is 6 meter multiplied by 5, that is 30 meter plus 333 plus is 1.5. So that is 34.5 meter length in the Z direction, and there's a bend here, and the pipe goes down by 0.9 meter, and then in the X direction there's 3 meter. Okay, so let's get started on a live demo on AutoPipe, and I'll explain how easy it is to complete this project from the scratch till the end. Okay. So I start with the AutoPipe software from the scratch. So I'm using the latest version of AutoPipe Connect Edition, version 11.3, and this is the first screen. So here I choose for those who do not have a license of AutoPipe, you can just install AutoPipe trial version, get it from one of our sales team or our channel partners, and you can finish this workshop just with the demo version of AutoPipe. Okay, because the demo version of AutoPipe supports up to 20 points, and this model is less than 20 points. Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 points only. So we can very well complete this hands-on exercise with the demo version itself. Okay. And these are the three versions of AutoPipe: standard version, which has all the basic features of StatPro, and the cheapest version; the advanced version, which includes the advanced features like buried piping and other advanced dynamic analysis; and then we have the nuclear version, which is the most expensive version of AutoPipe, which has the nuclear codes. And both these versions supports stress isometrics as well as AutoPipe Nozzel. The standard version doesn't have those features. Okay. Nearly 80% of AutoPipe users around the world use the AutoPipe advanced version. The remaining 20% use either standard or nuclear. Okay. So usually for a serious stress pipe stress analysis engineer, usually they choose AutoPipe standard version. Okay, so for this example, you can either use the demo version or one of the licenses of AutoPipe. Okay. And the help menu of AutoPipe is equipped with tutorial problems, workbooks, as well as manual, which has step-by-step instructions for getting started in AutoPipe, and how to produce stress isometrics, and modeling approaches for anchors, bends, almost every piping component, and also some example problems for advanced features like buried piping, water hammer analysis, and steam relief analysis and harmonic analysis. We also have our technical support through various methods. One of the important way of communicating with our support team is by raising a service request. Okay. So and also another easier method is to use a Bentley community site. Here we have forums and wikis and blogs. Also, another important resource is this frequently asked question. So here we have nearly 121 questions already answered. Frequently asked question in AutoPipe already answered here right away in the manual. This workbook contains the modeling approaches which we just saw in the manual also. Example systems. Okay. And this tutorial contains a workshop kind of tutorial similar to the one which I am presenting. Okay, so here's where the first screen of AutoPipe. Here you can see the coordinate of AutoPipe. Y-axis is elevated. Y-axis vertically up, similar to StatPro. But if you want to change Z-axis up, you can do that. Okay, by using one of the settings. But now we'll start with the file new, and I give a file name as say tutorial 1. Okay, and the file extension is .dat. Okay, so here's where we have the option to register a project in the cloud and then upload your model to the cloud so that you can share the same model to the users around the world whom are invited to this project. Okay. But for this example, I'm going to store the model in a local computer, so I'm not going to use this cloud project, so I'm going to close it. And in this screen, I'm going to select the piping code as ASMEB 31.3 process, and the latest code 2016. You can see you can go back all the way up to 2004. And the units, I'm going to use SI units for input and output. And the vertical axis direction, as I said, you can change it to Z axis, or by default you can leave it to Y axis up. Okay. Ambient temperature, room temperature, we leave it as 21.1 degrees Celsius. As soon as we choose the unit as SI units, this temperature units will be centigrade. Okay, degree centigrade. If you use English unit, okay, or AutoPipe unit, then this will be degree Fahrenheit. Okay. Okay, so libraries, we use AutoPipe component library, but you can see the other component library like Japanese and other country library. Okay, material also we use the ASMEB 31.3 2016. Okay, so with that input, the next screen asks you to start routing your piping. I start routing my piping with an offset of 900 mm above the ground level, because here you see the bend here which goes 900 mm. Okay, so I'll assume this level as ground level, so that all this piping will be above the ground level of 900 mm. Okay, and the pipe diameter I use 200 STD, 200 mm STD. This is just a name. The program at this point of time does not understand what is this. So when I press OK, it gives me this pipe properties dialog and asking me to fill up the details about this 200 STD. Okay, so in the nominal diameter field, you see NS means non-standard. Okay, so I'm going to use a standard pipe. So I'm going to use 200. So instead of using NS and manually typing the actual diameter, I'm actually choosing a standard 200 mm nominal diameter. And choose the schedule as standard. Okay, and you can see the wall thickness and actual outside diameter is filled up automatically. And as I said before, I'm going to skip this corrosion and insulation thickness, cladding thickness as well. And specific gravity of contents, let's assume it as water. Okay, water as the fluid. And the piping material is, I choose here as A53 grade B. Okay, and as soon as I choose the piping material, you can see the allowable stresses, the yield stress and ultimate stress are filled up automatically. So with that, here the next dialog asks me to fill up the pressure and temperature. So I'm going to use 1.7 degrees, 7 Newton per millimeter square as pressure. Temperature is 270 degrees Celsius. Okay, let me go back to our PDF file to verify this temperature. I'm sorry, the temperature should be 370 degrees Celsius instead of 270. Pressure is 170. Oh, sorry, 1.7. Okay, so let's assume we made a mistake here of 270 and press OK. Okay, so it's very easy. You can see the spreadsheet here. All the inputs you fill up here, it goes in here in the spreadsheet format. Anytime you can come back here and modify this temperature to 370 degrees Celsius. Okay, so this is our origin, and we have 900 mm above this origin as the starting point A00. I'm going to start insert run. First one is 6 meter in the minus Z direction, so I use minus Z and 6000. The units you can always see at the bottom right side corner of your screen is millimeter. Okay, so 6000 mm, and from here there's another run which is 3000 mm in the same direction. Okay, and from here onwards there is a multiple run of the same length, 6 into 1, 2, 3, 4. So instead of creating it one by one, I'm going to create a multiple runs of 4 runs of minus 6000. Okay, 10. And then run dy is minus 900. Then another run which is in x direction, which is 3000. Okay, note that there is a bend here and here, but I have not created a bend. Instead, I created runs. Okay, let me fix that easily later. I purposefully did it. Okay, I'm going to insert an anchor point here. Anchor. Okay, rigid anchor. Okay, so I already inserted, and I forgot to insert an anchor point at the starting. Okay, so I select this point, insert anchor. Okay, note that we have option to specify as flexible or rigid anchor. So this example I used rigid anchor, and we also have option to specify the thermal anchor movements. If you know the movement of the pressure vessel here, the thermal expansion of the pressure vessel, then those expansion you can specify it here. Okay, and if you want to design the nozzle which is connecting the pressure vessel and the piping, you can click this button so that after the analysis you can export to AutoPipe nozzle. Okay, and we also have another software called AutoPipe Vessel to design the pressure vessel itself. Okay, and the nozzle forces can be exported directly from AutoPipe to AutoPipe Vessel software as well as AutoPipe Nozzle. AutoPipe Nozzle is free to use software for AutoPipe Advanced and AutoPipe Nuclear license. Okay, it doesn't come with the AutoPipe Standard license, only for Advanced and Nuclear. So I created the anchor point here. Okay, so now let's look at this bend points. Okay, so before that I show this in 3D view. Okay, I can see this ugly bends. Now select this bend and use a shift key to select the other bend, so that the piping segment between these 2 points is getting selected automatically. So I'm going to modify, convert point to bend. That's it. You can see the bend is now good. Now you can select each bend and modify the bend type here. It's long or short. Okay, that's it. We finished the modeling very quickly within few minutes. Okay, now I'm going to model the supports. Let's have a look on our PDF file. So here we have a vertical stop support in A01, A02, and there's a guide support in A03. A V-stop again, a vertical stop in A04 and A05, and a guide support again in A09. Okay, so they're basically 4 V-stop support and 2 guide supports. I made a mistake here in not modeling this small segment of 1.5 meter here. So let's see how I fix this mistake. Okay, so first I choose this point. Let's first dimension our piping. Okay, so here's 6 meters. So we need to select this point, use shift key, select this point, and then use modify, stretch. Let's see, where is the stretch command? Okay, if you're not able to find here, we can always use this search command search utility, and just type in the few letters of the command, and there you got move stretch. This is in the home menu, operations, move stretch. So directly I can double click here to open the dialog like this, then I get this command. Otherwise I can go back to the home, which it guided me, home, look for operations. So operations is here, and look for the stretch command, this one, move stretch. Okay, so very useful command here. For new users of this Connect edition, if you find difficulty in searching through these icons, you can always type in this command. Okay, very handy, move stretch. Okay, so I'm going to move this part of the pipe, to be exact, stretch by 1500 mm in the minus Z direction. Okay, so that way I fixed my mistake very easily. Oops, sorry, instead of 1500 I made 4500. So undo. As long as we have undo command in AutoPipe, there's no problem to make mistakes. So minus 1500. It's good that I make mistakes during the training here, during the workshop here, so that we learn how to fix that mistakes. Okay. So note that I made another mistake here. Before stretching this to another 1.5 meter, I should have created a point here. Okay, but it doesn't matter. Now it's very easy to fix this also. Just select the nearby joint and say insert, run, and specify the length is minus 6000. Actually, we are not creating a run, we are just creating a node. AutoPipe behaves like a rubber band. Okay, so when I create a run from here, it knows that it's already there is a pipe run here of 7.5 meter, and then it creates only one node here at 6 meter. Okay, and there we got the 1.5 meter. Okay, so it's so easy to create this model, and now it's time that we start creating the supports. Okay, so I switch off the unnecessary things and switch on only the node number. So it's easy. Maybe node points, point symbols may be useful. Okay, other things we can switch it off. Okay, so now I'm going to select A01, A02. Okay, so you can see that the selection at the bottom right side corner. Okay, A01, A02. You can see them highlighted in red color, so you can use the control key and then use the control key, not the shift key. A04, A05. Okay, let's go back to the PDF file to verify. A01, A02, A04, A05, and here the numberings are later on, we can renumber it later. Okay, so you go insert and select support. You're going to use V-stop support. Okay, connected to ground, 0. So this example, I'm not going to use any gaps. Okay, I'm going to use a bidirectional V-stop, vertical stop support. If you want to use a unidirectional support, you can just specify a large gap above the pipe, or you can just use shoe support. Okay. Okay, and if you have if you want to design a hanger, you can use this rod hanger option. Okay, so that's it. One operation we created 4 supports. Okay, V-stop support. Now to clear this selection, you need to go to select and hit the clear button. Okay. Now select A03, control key, and A09. Okay, and then use insert support. This time we use guide support. Have a look on the other support types offered by AutoPipe. Okay. So that's it. We finished our support. Okay. Now, if required, we can do the renumbering. Note that here is the numbering is all good, but here we made a mistake. So after A05 is A09 and then A06. So to fix this, you can renumber it, but it's not always mandatory to do this. But it'll be easier if you have the numbering under control. Okay, so I select all points and then renumber. I can go to home and look for operations and look for renumber. Or if you find it difficult using the menus, you can use this search command utility and type in renumber. Okay, so here we have renumber all points. Okay, so yes, and now we can see the renumbering fixes the problem. A09 is here. Look at this spreadsheet, it's got populated now, and here we can see the pipe component properties, pipe properties. Here we can modify the diameter and schedule, okay, anytime. And we have only one segment, but if you have multiple branches, you can, this segment becomes a very handy tool. You can switch on and off a particular segment and apply wind for segments, only particular segments, and but not all. If you want to modify the coordinates of the piping, you can modify using this coordinates here, or the lengths, the anchor support. You can modify the type here. Other supports like V-stop and guide support, anytime you can change the support. You can modify the friction coefficient. Okay, and the bends, we do not have any walls or flanges in this example yet. Okay, so this spreadsheet becomes handy, very handy for modifications. Okay, so now that we have finished the analysis, I cleared the selection. Now I need to analyze it. Okay, run the analysis, go to analysis menu, and use this load case description, and see that in our example we have gravity load, thermal load, and pressure load. Okay, and only one temperature and pressure load case. If you want to add multiple temperature pressure load case, all you need to do is go to this general options in the tools menu and specify this number of thermal pressure load cases as more than one. Okay, for this example, let's leave it as one. Okay. So the program gives me some warnings. Let's have a look. Following inconsistent data, number of load cases does not match. Okay, number of load cases does not match. So let's go back to make sure the general options as we are left with one. Okay, yes, and case 1, this is the case 1 temperature, case 1 pressure. It's all good. Okay, select clear, go to analysis one more time. Last time we already saw the load case description. Static analysis set, select this is the number 1 analysis set, which is automatically created, and here you can see the gravity, temperature, and pressure is selected. You can hit the modify button, make sure the gravity is selected, temperature is selected, and pressure is selected. And if you have gaps in your supports or friction coefficients specified or soil supports, you need to click this button, which will automatically trigger a non-linear analysis. But for this example, we just do a linear static analysis because we do not have any gaps of friction or soil supports. That's okay. Okay, and then run the analysis by hitting the yes button. Okay, so the program comes up with this option, and you see that static analysis alone is checked in. Okay, within a blink of a second it finished the analysis. Now I can go to the results and core stresses, ratio, press OK, and now we can see the color coded ratio. Okay, this is a ratio, not the real stresses. Okay, ratio means the actual to allowable stresses. Okay, so what we see here is red color. Red color means is greater than 1 ratio. Greater than 1 ratio means is failing. So the maximum ratio is occurring somewhere here, and to see it more clearly, we can go to the show menu and switch off this point name, so I can see the ratio here, 4. Okay, so that 4 means the stress here is 1199, 1200. Okay, 1900 to be exact. 1199.32 divided by this allowable stress of 299.42. So that is 4.004. Okay, that's exactly this ratio. 4.01 rounded off to 2 decimals. Okay, and this ratio is the maximum. Is caused due to the expansion stress, and let's have a look on the sustained stress. Its ratio is only 0.15. the hoop stress is only 0.22. So that means this system is failing because of one reason, and that is the temperature, which is causing this huge expansion. Let's find out how much is expanding. Let's go to the result and find out the displacement. Have a look on this thermal load case, because that's the important load case, and I'll see the animation. Okay, and you can see this 35 meter, approximately 30 meter length pipe is expanding, and this animation shows you the behavior, but let's have a look on the numbers. Let's select here this point, and here you can see the displacement is 150 mm in the z direction, minus z direction. 150 mm. Wow. Okay. So let's see whether that is the point which is having maximum reflection or not. To check that, let's go to results grid. The grid, what you're seeing here, the spreadsheet, what you're seeing is just the input grids. What we need to see now is a result grid, which is similar to this. Okay. And this result grid, I can sort this table in resultant displacement by double clicking here. Okay. 158 millimeter is the maximum. When I double click it first time, it sorts in ascending order. When I double click it here for the second time, it sorts in descending order. Okay. Displacement in x direction, displacement y, z, and the dr is the resultant displacement for combining all these three. Is 158 millimeter. Okay. And using this filtering options, I can switch off and investigate case by case basis. So see that gravity deflection is less than a millimeter, so that's not significant. Thermal is the one that is causing all the problems. Okay, and pressure, not at all a problem. The combination is just this because of this expansion, thermal expansion, 158. Okay, so this is the load that is causing all the problem for the failure. Okay, so this feature is a very useful feature for filtering out the results of displacements. The same way we can investigate the forces. Okay, anchor reactions, support reactions, core stresses, and dynamic analysis results. Okay, and general stresses as well. Okay, so now that we investigated the magnitude of the displacement 158 mm, let's think about how do we solve this problem. Okay, one easier method of solving this problem is by putting an expansion joint here. Okay, so exactly at the middle. So let's select the nearby joint. Okay, and use insert run. Okay, 3 meter. Automatically the program automatically suggests you with the length of half the length of this pipe segment. This segment is 6 meter. Automatically suggesting you 3 meter. Okay, let's say okay. So now we got a point here, a node, and that's the point where we are going to insert our flexible joint. Okay, this is the expansion joint. Okay, so here we need to specify the axial stiffness and the length. The length for this expansion joint. In this case, let's assume it is around 300 mm. Depending on the manufacturer, this length may vary, and the axial stiffness approximately I try with a 500 Newton per millimeter. So you can see the units here at the bottom right side corner is Newton per millimeter. Okay, axial stiffness. Rest of the fields I'll leave it as rigid, because this the important input for this flexible joint, the bellow or this expansion joint is 500 Newton per the axial stiffness, which is 500 Newton per mm. What that means is, if I apply 500 Newton load, that will cause 1 millimeter deflection. Okay, 500 Newton is just 0.5 kilonewton. That is 5 kilograms. If I apply a 5 kilogram load, that will cause 1 millimeter deflection. It's a very, very soft spring. Okay, let's see whether that solves the problem. Just a trial and error. Okay, so I'm going to use this small flexible joint, and let's see whether it solves the problem. I run the analysis one more time, look at the results, force stresses, ratio, press OK, and now you can see it almost solved the problem, and now we have 1.48. Last time we had a ratio of 4, okay, but still it's not fully solving the problem. So what I'm going to do now is to play with the spring stiffness of this expansion joint. Instead of 500, I'm going to change it to 750. Okay, that means a little bit increasing the stiffness of the expansion joint, and going to test it out. And and now the ratio has increased 1.88. What does it mean? That means the stiffness has to be reduced instead of increasing. Okay, so I go back to this expansion joint and modify this spring stiffness again. Instead of increasing it, I'm going to decrease it to 250 Newton per mm. I make it even more softer. Okay. Run the analysis one more time and look at the results. And now we have 0.8. The problem solved. Okay. But many piping engineers don't like this expansion joint because it is expensive and requires a lot of maintenance. Okay. So let's try for look out for a different solution. Okay. Let me delete this flexible joint. Even the node, just select the node and delete it. Okay. AutoPipe will delete the joint and stitch the piping. It behaves like a rubber band. Okay, so now let's think of putting an expansion loop instead of expansion joint. So select the nearby joint. Okay, start routing your piping. Insert run. Okay, and the total length of this segment is 6 meter. I'm going to create an expansion loop 1 meter from here, and then moving up 1 meter, and then the loop length of the loop is say 4 meter or 3 meter in x direction, negative x direction. Okay, so let's start. Okay, so y direction, sorry, x direction, sorry, z direction minus 1 meter. Okay, it's 1000 mm. You can see the units here. Okay, so I create a joint here, then create a run. This time is minus 1000 mm above. Okay, the run. This time it is minus, sorry, not the z direction, sorry. It should be the x minus x direction. Let's carefully watch this. Let me cancel it and show you. We are going to create a loop in this direction, which is minus x direction. Okay, so insert run minus 4 meter. And the remaining fields use 0 and remember to use the tab key to update this field. Okay, so that's why here I create a run one more time. This time in the z direction, minus 4 meter. And other fields make it as 0. Okay, and remember to use the tab key. That's it. And now come back here. So one more run. This time is in the positive x direction, which is 4 meter, 0, 0, 0. Okay, remember to use the tab key. Note that we didn't create the bends here, which I'm going to fix it later, like the same way I fixed it here, modified the joint as bend. Okay, we'll do that same here later. I'm going to insert a run here. This time is minus 1 meter, 10. Okay, so select this from this point till this point and modify, convert point to bend. Done. So let's see whether this expansion joint helps. But before that, I want to put a support here because a 4 meter length pipe, we definitely need a support here. Okay, so select a nearby joint and insert a run of at the middle. So 4 meter divided by 2 is exactly at the middle, 2 meter. Okay, so I insert a support here. The V-stop support will do. Done. And rerun the analysis. Let's look at the result. Go stress. And now you can see this solved the problem, 0.97. Okay, so we found an alternate solution for this, and let's see the reports. Okay, so results, output report, and we can select all that's required for the output. We can also filter this to selected components of your piping. Right now I'm not using any filter. So I'm going to select for all. Okay, so increase the font size, and this is the output report. Okay, so you can see this results of displacements of the joints and support forces, both in local and global directions, restraint reactions, global forces and moments, again in both global and local directions, and finally the code compliance report. This is very important. So here where at each point you get the code stresses and the allowable stresses here. This is the equation number here and the load type. here's the load combinations. So usually it is this code allowable divided by the code stress. Sorry, the code stress divided by code allowable will give you the ratio. Okay, and here we see the summary. So here we get the maximum reflection. So now the maximum reflection is 75 mm. Remember last time we got double the amount, nearly 150 mm. By putting in an expansion loop, we reduced it to half. And here we have the maximum restraint rotations and forces and moments. And here we have the maximum pipe forces in newtons, maximum pipe moments in Newton meter. And here we get the ratios, result summary. This is very important. Okay, so the ratio for maximum sustained stress is 0.21, which is well within the allowable limits of 1. And the displacement stress is 0.97, as we saw graphically, which is the governing one. And the maximum hoop stress is 0.22. That is caused due to the pressure, hoop stress. Okay. So sustained stress is caused due to the gravity plus pressure. Displacement stress is caused due to the temperature. Okay, the temperature range. Difference between the ambient temperature and the operating temperature. So the hoop stress is caused by the internal pressure. Okay, so now at the bottom you can see here the system. The program reports that the system satisfies the code requirements for the selected options. So we finished the project. Okay. And now let's produce a stress isometric drawings. Okay. So I go to File. Save as. Save stress isometric. Okay. Give a file name. By default, use the same file name as the AutoPipe model with the extension of DGN. Okay, you can also save it as a DWG file or DXF file or 2D DGN. Okay. So now when I save ES, since I use AutoPipe Advanced license, this stress isometric will be created using the Open Plant Isometric Manager. If you use a demo version, you won't be able to use this functionality. Okay. So here's the data editor for your stress isometric. I leave it to default. You have options to edit it here, okay, but I leave it to default and press OK. Now at the background, the Open Plant Isometric Manager is running. This is given free along with the AutoPipe Advanced and Nuclear licenses. The DGN file is generated. And since I configured the AutoPipe program to use Bentley Navigator as the viewer, it automatically gets opened up to view the stress isometric. But you can configure it to use Bentley View or any of the CAD programs that you have in your office. For your information, Bentley View is free. And here's the stress isometric, which gives you the isometric drawing in 3D. Okay, it's actually a 3D model. Okay, and here you can see the annotations, the bends, for the supports, the loads. This will be very useful for the structural team if this piping is sitting on a pipe rack. Okay, this will be useful for structural engineers to design the pipe rack. Okay, so all the information about this piping system is here. Okay, so let me close this. Okay, we also have a comprehensive flange check module using which you can design the flanges, and we can export this nozzle loads to AutoPipe nozzle to design your nozzles. Okay, so now AutoPipe nozzle program is getting opened up, the license is being checked. Okay, and now you see this AutoPipe nozzle ID is shown up, A00. Last time we forgot to check selected. So import loads into existing model. There's no need because We started from the scratch, so no need to press OK. So now we can choose the nozzle direction. Okay, so I leave it to default horizontal or vertical. Okay, choose horizontal, press OK, and then specify the material, shell material. Is A36P. Similarly, I go for nozzle and specify the nozzle material also. Reinforcement pad material also. Geometry, we'll use the default geometry here. In addition to that, if you have any projections, you can specify here, and this diagrams will help you to specify this projections of the nozzle. Next, the loads all got imported from our model: gravity, temperature, and pressure. Okay, and here you can specify the factors, the safety factors, and here you can choose the code of the design code here. So we use WRC 107 code, and you can see the other available list of codes. Okay, so next is to do the load combinations. So I go to the loads and specify the load combinations. These are the three load cases we have: gravity, pressure, and temperature. I go to auto load combination, hit the auto button, the combinations automatically done. Okay, so we have two combinations. Okay, I don't have any user combinations. Okay, press OK. That's it. We have selected the load combinations. We have selected the code here. We have specified the material for the nozzle, shell, and reinforcement pad. All we need to do is now analyze the stresses. Okay, now you can see all the stresses are analyzed, and you can see the actual stresses and allowable stresses, and here's the percentage, all shows up in green. The percentage less than 100 means is passing. Okay, that completes our nozzle design as well. Note that this nozzle design will be available only if you have AutoPipe Advanced and Nuclear licenses. It doesn't work on demo version or standard license of AutoPipe. Okay, so with that, I'll end my hands-on workshop for AutoPipe. Hope you enjoyed it. Please keep in touch with me if you have any doubts. My email address is madhan.elumalai@bentley.com.